All right. I this is the this will be a little bit shorter, but anyway, this is from your book. This is actually on page 86. So it says, suppose that the mass of a spacecraft in Figure 4.7. All right. So basically, what they're doing is they got a guy pushing on the spacecraft. He's doing a spacewalk. All right. He's doing a space. Why do I try? Why do I try? All right. Anyway, sorry. So sorry about that. Um, so there's a guy out in deep dark space. He pushes on his spacecraft. All right. Um, the mass of the spacecraft is 11,000 kilograms, and the mass of the astronaut is 92 kilograms. In addition, assume that the astronaut pushes with a force of 36 newtons on the spacecraft. Find the accelerations of the spacecraft and of the astronaut. This is just like the book and the Earth problem. Okay. Now, I have to confess, I was really screwy even when I was teaching this course for a long time on Newton's on this third law, because I myself would get confused between what is a net force and what are the action reaction forces. Okay, that's a little better. All right, so here we have. So you got the spacecraft. Okay, and you've got this little astronaut out here floating around. He's going to push on this spacecraft. All right, he's the mass of the astronaut, 92 kilograms. Mass of this thing is 11,000 kilograms. All right, he pushes with a force 36 newtons. That's going to get that thing to move. It will move, not by much, but so will he. So we have two action reaction forces. Let's figure out what they are. Okay, so free body diagram of the astronaut. Free body diagram, big friendly giant. Free body diagram of the spacecraft. Okay, so the astronaut has a reaction force of negative 36 newtons. The spacecraft has the force of 36 newtons. That's the force acting on the spacecraft. This is the force acting on the astronaut. Okay? So the acceleration of the sum of the forces acting on the astronaut are equal to negative 36 newtons. So the acceleration of the astronaut is equal to negative 36 newtons divided by his mass. Which would give us negative 0.39 meters per second squared. And then we'll do the same thing. The force on the spacecraft is equal to 36 newtons. So the acceleration of the spacecraft is 36 divided by 11,000 kilograms. That's going to be dinky. 0.0033 meters per second. And that's positive. All right, so the astronaut goes flying back this way and the spacecraft barely moves that way. Here's an interesting question. How far apart will they be? How far apart will they be in 5 seconds? So, here's what we've got going on. Besides Stacy's mom. No, kidding. All right, anyway. I've got the astronaut going this way, accelerating at negative 0.39 meters per second squared. If we count this as ground zero, and I've got the spacecraft. Now he's going to be going like this, and I got the spacecraft accelerating this way at 0.003 meters per second squared. Ah, well, the displacement of the astronaut then is going to be x final is equal to x initial plus the 1/2 the acceleration times t squared. Because I gave you the time. Okay, well, x final then is equal to 0 plus 1/2 of negative 0.39. Some of you might have said, well, wouldn't you use the minus? All right, I stuck it in here. 0.39 times 5 squared. And so his distance is 0.5 times negative 0.39 times 25. So he went negative 4.88 meters this way. So he's over here at negative 0.488 meters, which could be trouble. I mean, he's 15 feet away from the spacecraft. Now then, and so this is for the astronaut. In this case, if he doesn't have a lifeline, he's an astronaut. But anyway, so now we've got the spacecraft. And everything we do is just kind of a variation of all these things. So now we have the spacecraft, and its x final is equal to same thing, 0 plus 1/2, but this time it's a positive 0.0033 times 25. So it's barely gone. So in those 5 seconds, the spacecraft went 4 centimeters. Okay, it barely moved. So the distance that they're apart, the change in displacement between the two is 0.041 minus negative 4.88. That equals 4.92 meters. That's how far apart, that's their display, that's how far apart they are. And you could have measured it from here to here and gotten negative too.